Rinsing causes EMI noise, decrease the performance of the system. In some cases, it will damage the system. It will damage the device. Rinsing makes the system unstable, so we have to do the stability test. We use the superposition theorem to define the transfer function in electronic system. The report comparison measurement is used to define the transfer function in linear negative feedback amplifiers. We investigate the Fermat-Jean at unity gain of the Sherlock function to determine the operating region of a linear network. The main contributions of this work are the superposition formula for multi-short networks and the concept of the Sherlock function in a transfer function. The Sherlock function is defined directly from the transfer function. First, we will review the operating region of a second-order system. Then we investigate the behaviors of a solution feedback amplifier, an inverting amplifier, and second-order Acrobat Modbus Ramat filters. In this work, we use the superposition formula to define the transfer function of a multi-short network, such as operational amplifier, polyphase filter, complex filters, and so on. The main advantage of this formula is that the output voltage can be expressed separately with the input sources, and all sources can be computed at one time. Now let's define the concept of the Sherlock function in a transfer function. In general, the transfer function of a network can be simplified as A of omega over 1 plus L of omega. Here, A of omega is the numerator function and L of omega is the Sherlock function. We use Nikon chart to plot the characteristics of the Sherlock function. Now let's review the characteristics of an adaptive feedback network. An adaptive feedback network is used to control the output shock along with the decision source. The loop gain is independent of the frequency variable because the reference voltage and the feedback voltage and the error voltage are direct current voltages. Therefore, the repulse Sherlock function is significantly different from the loop gain. In general, a circuit can be simplified as an input shock, an input impedance, and an output impedance. The Sherlock function is defined as Z in over Z out. In practical measurement, the Sherlock function is derived from the numerator function and the transfer function. There are three steps. First, we measure the numerator function A of omega. Then we measure the transfer function A of omega. And then we define the Sherlock function. This work overcomes some limitation of the conventional methods. The middle roof measurement of the loop gain is only used in DC to DC converter. The replica measurement of the loop gain cannot be applied in the practical measurement because we have to use two identical networks. The Nyquist stability condition do not show the operating region of a linear network. Nikon chart is not widely used in the practical measurement. Let's present the rinsing test for feedback amplifiers. This table shows the summary of the behavior of a second-order transfer function. In case of overdamping, the magnitude of the transfer function is greater than -6 dB. This gain will amplify the high-order harmonics at around the cutoff frequency and cause the distortion of the signal. The characteristics of the Fermat-Jean at unity gain of the Sherlock function of a second-order Sherlock function are summarized in this table. In case of reticle damping, the Fermat-Jean is 76.3 degrees. If the Fermat-Jean is smaller than 76.3 degrees, the rinsing occurs and makes the system unstable. Let us show three typical examples of a second-order system. In case of underdamping, the magnitude of at the cutoff frequency is 0 dB, and the Fermat-Jean is 52 degrees. The rinsing occurs in the transient response. The characteristics of a shunt-to-shunt feedback amplifier are described in this slide. after applying the superposition formula at each node in the small signal model of the amplifier, the transfer function and the shallow function are second order complex function. On the body plot of the transfer function, the magnitude at the cutoff frequency is 17 dB, and the phase margin at unity gain of the shallow function is 86 degrees. This amplifier operates in overdamping region. Now let us present the reason test for operational amplifiers with feedback loops. With down frequency compensation, the transfer function and the shallow function of a second state of the two state of M are second order complex function. When the two state of M were used to design a unity gain amplifier, the magnitude of the transfer function is very large, 15 dB, and the phase margin is very small, 13 degrees. As a result, the rinsing makes the distortion at the output signal. After doing the frequency compensation, the transfer function and the shallow function are fourth order complex function. Assume that A of omega is the open loop function of the two state of M. The value of Muller capacitor and resistor will determine the operating region of the unity gain amplifiers. The transfer function and the shallow function are shown in this equation. In case of underdamping region, the magnitude of the transfer function is 5 dB and the phase margin is 30 degrees. Therefore, the rinsing occurs in the transient response. When the two states of M were used to design an inverting amplifier, the transfer function and the shallow function are shown in the equation. Now, the magnitude of the transfer function in case of underdamping region is 20 dB and the phase margin is 41 degrees. As a result, the rinsing occurs in the transient response. Let us present the rinsing test for high-order robot filters. In this work, we introduce a fully differential form of the aqueous Morpeth robot filter. The transfer function and the shallow function of this filter are second-order complex functions. We use different value of the resistor to change the operating region of the robot filters. This slide shows the simulation result of the proposed design circuits. The magnitude of the transfer function is 15 dB in case of underdamping region, and the phase margin is 45 degrees. Therefore, the rinsing occurs in the time domain. This slide shows the measurement setup for the implemented circuits. This is the block diagram of the measurement setup for the device under test. A network analyzer and a laboratory power supply were used to perform the measurement. This slide shows the measurement results of the implemented circuits. In case of underdamping region, the magnitude of the transfer function is 20 dB and the phase margin is 64 degrees. So the rinsing occurs as shown in the transient response. Let's move on the final part. The comparison measurement were also used to compare with the existing methods. In this work, we measure the shallow function in a transfer function. The replica measurement and the middle loop methods were used to measure the loop gain. It is very difficult to optimize the behaviors of a linear system using Nyquist and Nikon theorems because the theoretical derivation and the practical measurement of the loop gain were not well explained. The loop gain in an adaptive feedback network is significantly different from the shallow function in a linear negative feedback network. In control theory, Nikon chart is only used in MATLAB simulation and it is not widely used in the practical measurement. We have introduced a comparison measurement for deriving the shallow function in a transfer function. The observation of the shallow function can help us optimize the behavior of a network. the theoretical concept of the ringing test are verified by the laboratory simulation and the practical measurement. In future work, we will do the ringing test for parasitic components in transmission line, rigid circuit board, physical layout laser. This is the reference. Thank you for your kind attention.